Hello everyone, my name is Jiazhou Liu. I'm a PhD student at Monash University. Today, I'd like to present about the design and evaluation of interactive small multiples data visualization in immersive spaces. First of all, a small multiple is a data visualization that consists of multiple charts arranged in a grid. This makes it easy to compare the entirety of the data. In small multiples, different data sets are represented using the same encoding. Thus, they provide an overview of the data, but also allow for comparison with minimal interaction and without overloading the visual working memory. As we can see from these two examples, on the left-hand side, it shows the development of the virus. The color indicates the change compared with one day before. In these small multiples, we can compare vertically for the difference between different countries on a specific day, or we can compare horizontally for different time series in a specific country. On the right-hand side, the green color means the cure rate, while the black color means the death rate. We can easily find a pattern such as Singapore got a good cure rate compared with other countries. On desktop displays, there must be insufficient screen space for effective small multiples. Research now has focused on large displays for collaborative use of small multiples. For example, in the InCube, the researchers use a circular layout to visualize small multiples, allowing the visualization of a large number of multiples up to 80. Apart from the small multiple size, large displays still only support the same flat grid layout available on desktop display. With VR or AR, other layouts are possible. Our design space investigation is motivated by several real-world use cases of data with a natural 3D embedding, which is difficult to present in small multiples on flat screens. The use of 3D visualizations for aircraft trajectories is very important as airplanes move in 3D space. In order to identify peak traffic period, it is important for the airport managers to be able to compare the traffic hourly, daily, or weekly. This image shows a single aircraft trajectory on the left and how it will look like in the small multiples visualization on the right. Each visualization represents the aircraft's departure and arrival space-time track in 1 hour at Melbourne Airport. Another example is BIM. With the use of the building information modeling format, facilities managers have more and more opportunities to visualize data coming from different building sensors overlaid on 3D CAD model of buildings. Those sensor data include temperature, pressure, and carbon dioxide. This image shows a single BIM model on the left and how it will look like in the small multiples. On the right, this model is from one of the Monash campus buildings. When looking at demographic data like population, GDP, spending in different areas, it is important to see both temporal and spatial evolution, for example by years and countries. The use of 3D bar charts in small multiples arrays allow for 4 dimensions of data to be viewed simultaneously, and potentially for trends involving more than 2 variables. While small multiples layouts have been explored in traditional flat screen implementations, there is no existing design space to describe such layouts in 3D space. In this paper, we proposed a design space for layout of an interaction with small multiples in an immersive environment. We also implemented a prototype system allowing us to explore layout and interaction designs. We then ran 2 user studies evaluating the effect of introducing curvatures such that use small multiples wrap around the user. Regarding the design space, we identified 4 design dimensions that describe many possible layouts of small multiples for 3D data immersive environments. For the dimension of the layout, a 1D display would be a single row. 2D is a traditional grid used on screens, while 3D is a new possibility afforded by immersive environments. Adding a depth dimension to the grid. Adding more dimensions allows more multiples to be compacted into a volume, but stacking the depth dimension will introduce occlusions. Curvature allows multiples to wrap around the user, reducing the need for walking, while curving a 1D layout is relatively straightforward. There are several possible ways to curve layouts in higher dimensions, for example, curving a 2D layout into a cylinder or a sphere. Aspect ratio refers to the number of multiples in each orthogonal dimension. For example, a 2D array of 12 multiples can be arranged in a ratio of 4 times 3, 3 times 4, or 2 times 6. Orientation refers to the relative orientations of the individual 3D data visualizations. Similar to flat screen 2D layouts, one might align all the layouts to the same forward-facing direction. However, with a curved layout, Rotating each visualization to face the user may help them to more easily make comparisons. After exploring the design space, we plan to use the shelves metaphor to provide cues for interaction. The shelf visuals provide affordances for users to understand and arrange 3D small multiples and provide clear horizontal and vertical alignment of the small multiples to enhance spatial memory. In addition to walking around the data and viewing it from different perspectives, users can reconfigure the small multiples layout by grasping and manipulating different components of the shelf's visible form. Affordances for layout comparisons are revealed to users by visual handles on the pillars or shelves, which also provide visual feedback during manipulations. By grabbing both front pillars simultaneously allows the shelf to be bent, adjusting the layout curvature. The shelves can be adjusted continuously between a straight layout and half-circle configuration. By grabbing one of the front shelf pillars, the shelving unit can be stretched or compressed horizontally. As the shelf width changes, the multiples automatically rearrange themselves to fit the new aspect ratio, with animated movements between shelf positions. There are more interesting implemented operations, such as changing the height of each row by adjusting the top point of the front pillars, and also changing the shelf's position by moving the middle transparent ball in the shelf. We also implemented several operations for interacting with the 3D data visualizations to allow us to investigate the use of the small multiples layouts with data analytics tasks. To view the data visualizations from different sides, users can press both controller triggers to present a view cube. Users can then manipulate the cube rotation, which is reflected across all multiples. Brushing allows users to select one or more data points on a single visualization, and see the selection linked across all coordinated views. We provide several brushing methods. Users can brush a single data point with a pointer that extends from the controller. Or they can use a bimanual interaction of a pair of sliders on any axis to brush a range in one dimension. Finally, a bimanual gesture within the data volume brushes a cube-shaped region on all three axes at once. It is unclear how the layout of small multiples in immersive spaces impacts performance of users in the visual comparison task. So we evaluate 3 different layouts with 2 different datasets for such tasks. Our design task consists of a visual comparison between pairs of visualizations that are part of small multiples display. To provide generalizable results, we include 2 common datasets in our studies. BIM, which contains data that has a spatial reference frame such as a floor plan, and bar, which is typically representation of multidimensional, non-spatial 3D data. We vary the locations of the multiples to compare within the grid, controlling for distance between the 2 that need to be compared. In the short condition, the 2 multiples are at a Manhattan distance of 2, meaning that participants can do the task with both multiples simultaneously in their field of view. In the long condition, the Manhattan distance were 4 or 5. We also test 3 layouts: flat, quarter circle, and half circle. We focus on horizontal curvature, similar to existing large displays. Here's one of the tasks that we designed, with a condition of a flat layout, a bar data, and a long-distance comparison. The example question is, in which year Australia had more food consumption than carbon dioxide emissions? The users will look at the food consumption chart first, and then they will compare with the carbon dioxide emissions chart using the analytics tools such as brushing. Here's another task with the condition of a half-circle layout, a BIM data, and a short distance comparison. The example question is, which sensor had lower temperature reading in July than in April? Users will look at April and July the BIM models and compare the values. For the measurement, we recorded completion time and accuracy for each trial. Participants' heads were tracked during the entire experiment, which we used to calculate the distance traveled during trials. Finally, we used the eye tracker to find the object they looked at. From this information, we count the number of times they switched between the 2 small multiples under comparison. The fact that participants were faster with the long condition than with short is interesting. This might be due to the learning effect that participants completing short first in each condition, but also due to only 12 small multiples being insufficient to really force much movement. On the other hand, participants were clearly faster in beam conditions than in bar, which is expected due to the number of candidate data points for comparison. Regarding performance in short, participants were faster with quarter circle for the beam dataset. No other difference were found regarding time or accuracy. The layout in the short condition probably does not impact performance. In long condition, participants were faster and more accurate for both datasets with flat layout despite reporting that they found they had to walk more. In fact, analysis of the tracked movements revealed only a small difference in movement. For the qualitative results, participants argue that it is less easy to find a position where users can transit between the two small multiples with a half-circle layout than with flat. Finally, participants stated that the flat provides a good overview of the data and that they can easily see all the multiples at once and keep them in their peripheral view when they focus on one, which is not possible with the other two layouts. The first user study indicated performance advantages of the flat layout, as it provides a broad overview without the need for rotation, despite the need for some walking. We conducted a second user study to determine whether these findings scale to a more extreme design, with a larger layout containing more small multiples from 12 to 36. To better understand the effect of participant rotation, we also included a full circle condition and removed the quarter circle layout. The three experimental layouts are flat layout, half circle layout, and a full circle layout. We used the dataset inspired by the world indicator dataset used for the bar condition in the previous study. Each multiple represented the value of 5 indicators for 5 countries for a specific year. Here's one of the 2 tasks we designed, with visual comparison between pairs of visualizations with a magnetic distance of 7 or 8. The example question is for Sector 3, which country in 1990 had a similar budget as France in 2008. So users will first highlight the Sector 3 and find 2 charts of 2008 and 1990 and compare the value. The second task we designed is finding maximum value for a specific bar. The example question is, which year did Australia have most budget on Sector 3? So users will highlight the Sector 3 and then highlight the Australia. And the only thing they need is to compare the height of the red bar. We use the same statistical method and take the same measure as in study 1. We cannot see significant differences between different layouts regarding time and accuracy. For the comparison task, this could mean that the better performance of flight in the previous experiment is countered here by the greater number of multiples. Its explanation is supported by the fact that participants had to walk a greater distance, costing additional time. Finally, participants preferred for both tasks the half-circle layout. Their comments explained that it was a good compromise between walking and rotation, and that it allows for an overview at a glance by taking a step back. Participants identified that rotation in the full circle layout was disorienting and made it harder for them to locate specific multiples. Similar to the half-circle layout, flat was appreciated for its easy-to-access overview, but the amount of walking necessary was considered as an issue. Our user studies revealed that the performance of different layouts is dependent on the number of multiples displayed. With a small number, a flat layout is more performant, even if it is not the user's preferred one, due to the amount of walking required. With a significant increase in the number of small multiples, the difference in completion time was less noticeable. However, participants complained about disorientation with full circle and that it made locating a specific multiple difficult. It was also an issue that full circle made getting an overview at a glance difficult. On the contrary, the flat layout allows users to easily obtain an overview of all the multiples, but it requires too much walking. Regarding all these issues, the half circle provided a good compromise and was preferred by participants. There is future opportunity to more thoroughly explore the curvature design space. For instance, vertical curvature and a spherical layout. It would also be interesting to study the impact of interaction techniques that avoid walking, like VR teleportation or virtual panning of the shelf. However, This may also be less natural, disorienting, and may impact any kinesthetic memory effect. During the study, a few participants stated that the disorientation in circular layout affected their spatial memory to memorize the position of specific small multiples. We are now running another user study to examine the impact on spatial memory using different layout. Thank you very much. That's all for my presentation.